We've got two small spheres hanging from threads. You charge the spheres up and they repel apart, and you get this equilibrium condition that's shown on the screen. So what you can imagine is you've got originally, just to put some context into this, you've originally got a couple of threads attached at this common point, and these two, and typically they're very, very small, and they're made of this styrofoam, very light styrofoam, and they're coated in kind of a carbon coating so they can hold a charge. They're called pith balls, P-I-T-H. And when you charge them up, of course, they both get the same charge and they repel apart. So that's what we're seeing to the left. So you've got these little tiny styrofoam objects moving apart like that. So it's equilibrium, which means nothing's moving. Now, you can see below, I've started the question with a free body diagram, but remember, in equilibrium, my net force has to equal 0, which means when I take all the forces acting on either the left ball or the right, doesn't matter which one, they're symmetrical. The forces acting on the left one, they all have to add up to 0. So let's identify them. On this picture, we've got our string, and our string, we know that's a tension force. We also know that the angle between the string and the vertical is 30 degrees. So I've got a little 30-degree angle. Well, let's label it on our original picture right here. So there's my 30 degrees with the vertical. Now, pulling the ball down is the force of gravity, which we have to include this time because this is not a single charge. It's an object with mass. I mean, not that a single charge doesn't have mass, but previously we've been not worried about the force of gravity acting on a single charge because the electrostatic force completely overwhelms it. But this has a significant mass in the molecular world. What's holding it apart is this repelling force, because both these objects are charged, and according to this, they're both charged to a positive 400 microcoulomb charge, like that. So they're repelling. So this is our electrostatic force. So those three forces, and they're all vectors, have to add to 0. And when I look at a picture like this, I immediately notice, okay, I've got 3. They've got to add to 0, so they got to make a closed triangle. And as soon as I see this little 90 degrees, I want to do tip to tail, because I know when I do tip to tail, it's going to be Pythagoras, it's going to be really easy. You could do it with components, and with components, everything's balanced. So you'd have a couple of equations. This x component for the tension would equal this would equal the electric force, the electrostatic force, the x's cancel each other. And this y component of the tension would equal Fg, and then you'd put those two equations together. But in my experience, if you've got 3 forces and you see a 90, it's way easier just to do tip to tail. So what are we doing? We're going Ft plus Fe, doesn't matter what order we add them in, plus Fg, all as vectors add to 0. So let's do that now. So I'm just going to grab these vectors and move them over if I can select them here. So there's my first one. And I'm going to grab it, drag it over. That one, plus Fe, so tip to tail, at the tip of my tension vector, I'm going to put the tail of my electrostatic force, plus force of gravity, like that. And then I'm going to adjust my picture because my original one was not to scale. I'm going to make sure everything lines up to make this triangle. Notice how I end with the force of gravity because I know it's straight down. That'll keep my diagram consistent because I know I've got to have a 90-degree angle between my electrostatic force and my force of gravity. Now, just for completeness here, I'm going to put this electrostatic force, I'm going to copy it and place it back on my original picture just so we can see what's going on. So the tip to tail diagram represents my free body diagram on the left. So let's label all the pieces once more. So I've got Fe here. I've got my force of gravity here. And I've got my tension force there. Now if you look at my sketch above, 30 degrees is right in there. So if I do that alternate interior angle thing, that's also 30, which is right here with the vertical. So there's my angle. Now the question's asking for the mass. What is the mass of those little pith balls? So I'm looking to find force of gravity so I can find mass. What else can I calculate? Well, I can't really get the tension directly, but I know how to calculate F electric. So we have formulas for my electrostatic force, and we have formulas for gravity. Gravity's the easiest one, right? We're assuming we're on Earth, it's just mg. My electrostatic force, the magnitude of it, is Coulomb's law. They're both spherical charges. So it's Q1, K, Q1, Q2, all divided by R squared. Now R's a little bit tricky. You got to do a little bit of geometry here, but at least the numbers are nice. They tell you that the length of the string is 2 meters. And we know that angle is 30 degrees. So there's a couple ways we can get the distance between those two charges. If that's 2 meters, I can make a triangle. See how that's 90 there? And this opposite side would be 2 sine 30, which is 1 meter. And the other side is symmetrical. That's also 1 meter. So R, 1 plus 1 is 2 meters. Notice that makes sense. If I look at the overall triangle, and let me just get rid of a little bit of clutter there. If I look at the overall triangle, it's actually an equilateral triangle. I've got 30 degrees here and 30 degrees here, so that's 60 degrees. These two sides are the same, so that makes an isosceles triangle, which means this angle and this angle has to be the same. So they're both identical. So all the angles have to add to 180. 180 minus 60 is 120. So these two angles at the bottom would have to add to 120. So we get 60 degrees again. So we get an equilateral triangle, which means all the angles are the same and all the sides are the same, which means this is also 2 meters. It doesn't really matter how you solve it. The first method or the second method makes no difference. Point is, I have equations for both. So now let's relate those two things together. We're going to avoid FT. So the last step we're going to use is tan. Tan of 30 degrees is opposite over adjacent. Now I'm going to put in my equations. So FE we know is K. Now Q1 and Q2 are identical. So that's KQ times Q, which is actually Q squared, all over R squared. That's the top of the equation. And the bottom is just mg. Now we're trying to solve for mass. So if I simplify this a little bit further, it's KQ squared, and the R squared can go on the bottom, times m. That all equals tan 30. So if I solve for mass, if I multiply both sides by m and then divide both sides by tan 30, I get my mass is equal to K Q squared over R squared G m times tan of 30 degrees. A little bit of cross multiplying there. Now I'll leave it to you to crank that through in your calculator, but I apologize for the answer. I described these little things as very, very tiny, like the size of a pea. Generally, for these kinds of experiments, they're the size of the pea, and they're made of styrofoam. And probably we should have worked this one out with the numbers I've given in the question. But when you work out with these numbers, you actually get a 64 kilogram object. So obviously, that's too big, right? I had too much charge on that thing in the first place. But the method is the same no matter how you slice it. So you get a 64 kilogram pith ball, which seems a little excessive.